Good day to my supervisor and my panels, Dr. Nur Anida binti Jumadi, Dr. Wan Mahani Hafiza binti Wan Mahmud, and Dr. Wan Suhaimizan bin Wan Zaki. My name is Darshini Anak Perempuan Ravindran, and my matrix number is AE180038. The title of my final year project would be Development of IoT-based Heart Rate and Oxygen Saturation Alert System in COVID-19 wards. Now, let me share a little bit on my project background. Coronavirus had emerged in Wuhan, China, and caused a massive outbreak across China and throughout the world. The disease was officially named as Coronavirus Disease 2019 by WHO on the February 11th of 2020. Coronavirus Disease 2019 COVID-19 is spread through large droplets produced during coughing and sneezing by symptomatic patients as well as asymptomatic individuals before having symptoms. A person with COVID-19 will experience a dangerous drop in oxygen saturation. As a result, medical oxygen had to be given to maintain the oxygen level within the usual range. The measurement of oxygen saturation is crucial in the management and comprehension of patient care. The National Institute of Healthcare recommends a target oxygen saturation range of 92 to 96% for COVID-19 patients. Oxygen saturation could be measured by using pulse oximetry, often used to detect hypoxemia. Pulse oximetry is based on the absorption characteristics of the oxygenated and deoxygenated hemoglobin in the red and infrared light. Oxygenated hemoglobin absorbs more infrared light and allows more red light to pass through, whereas deoxygenated hemoglobin absorbs more red light and allows more infrared light to pass through. Patients' heart rate may become rapid or irregular as a result of having COVID-19. Pulse oximetry is a valuable tool for determining a patient's oxygenation state and can be utilized in a variety of clinical settings. Pulse oximeter detects SpO2 is based on the amount of red and infrared light absorbed. Pulse oximeter offers a fast, easy, and non-costly technique. In comparison to blood gas analysis, the pulse oximeter offers about no blood samples taken, which is particularly convenient. The Internet of Things, or IoT, is a network of computer devices, mechanical and digital machineries, goods, animals, and people with unique identifiers, and the ability to transfer data without human or computer contact. The IoT helps healthcare centers to reach about to many individuals at once and provide good healthcare at a low cost. Next, I would like to share on the problem statement of my project. Due to the high number of COVID-19 cases daily, healthcare workers are getting tired, both mentally and physically, as they are required to work for long hours with minimum rest. Therefore, there is a constant need to attend COVID-19 patients one-to-one in getting their oxygen saturation level and heart rate readings from time to time. This project of alert system in hospitals will help our healthcare workers to always keep an eye on their patients' oxygen saturation level and heart rate reading, and to even act immediately when they are alerted by the system. The hypothesis of this project is it is an alert system which is developed to help the nurses and doctors to manage and attend the patients immediately when they are alerted of a drop in the oxygen saturation reading. The expected outcome of this research will be an alert notification given out that can help in reducing the reflex time of the nurses and doctors. Next would be the aim of my project would be to develop the IoT-based heart rate and oxygen saturation alert system in COVID-19 ward for COVID-19 patients. And the objective of my project is to develop the heart rate and oxygen saturation system, to develop the alert notification system using a buzzer and ThinkSpeak, and to evaluate the performance of the developed system. Next, I would like to share on the scope of the study of my project. So there are three phases involved in the scope of study. Phase 1 would be the hardware development, in which this project would be developed by using the MAX30102 pulse oximeter sensor, Node MCU ESP8266, OLED display, ThinkSpeak, and buzzer. The second phase would be the software development by using Arduino. So the MAX30102 sensor will be interfaced with the Arduino programming. The API key generated by the ThinkSpeak will be then added to the program code. The limitation of oxygen saturation level will be added in the coding too for the buzzer to function. The OLED display and the ThinkSpeak will display the heart rate and oxygen saturation reading. If the SpO2 percentage is below 92% or the heart rate reading in BPM is less than 60 or more than 100, the buzzer beeps and the notification are sent as an alert sign, and there will be a drop in the graph displayed or a rise in the graph displayed on the ThinkSpeak. The third phase would be the evaluation of developed system phase. in which the fingertip pulse oximeter will be used as a reference measurement. SpO2 less than 92% or SaO2 less than 90% are the indicators of hypoxemia. Hypoxemia is a condition in which the blood oxygen level are lower than normal. The body may not function correctly if the blood oxygen level are too low. Therefore, hypoxemia can result in minor symptoms like headache and shortness of breath. This project will be tested by a normal person without any symptoms of COVID-19, as it is very risky to test it on a real COVID-19 patient. The research contribution of my project would be for a better management system of COVID-19 patients in the ward, and to enable the nurses to pay and to give proper care and attention to those patients that are in critical situation, thus increasing the chances of recovery. Next, I would like to explain on photophlatysmography. Photophlatysmography is also known as PPG, and it is a low-cost and easy optical technique to detect blood volume changes in a tissue's microvascular bed. So it is frequently used to take non-invasive measurement on the skin surface. So the technique is performed by using a pulse oximeter that has two light sources at two different wavelengths, which is 660 nanometer for the red light and 940 nanometer for the infrared light. So the PPG in transmission mode uses a light source opposite a receiving photodetector that detects the light transmitted through the tissue. The pulsatile component of the PPG waveform is commonly referred to as the AC component, and the advantage of PPG is it is able to monitor peripheral blood flow in a non-invasive and continuous manner. So the next slide shows a signal and waveform of the PPG. So this is the PPG signal, pulsatile AC component and corresponding electrocardiogram, and this is the pulse oximeter waveform and arterial pressure waveform that is affected by the blood loss. Next, I would like to explain in detail on my sensor, which is the MAX 30102 pulse oximeter sensor. So this sensor consists of two LEDs that are paired with a photodetector to improve optics, and it has a low noise digital signal processor. So this sensor consists of 14 pins, and the function of this sensor is to measure a person's heart rate using a technique known as photophlatysmography, PPG. So the advantage of this sensor is it can distinguish between the light reflected by the blood in an artery that creates an AC output and the light reflected by other bodily components such as bones and tissues that produce a DC output. So the LEDs in this sensor they consist of varying wavelength, and this sensor is able to combat the issue of skin tone discrepancies. So the peak wavelength of the red LED in this sensor is 660 nanometers, and for the IR LED is 880 nanometer, and the LED pulse width can be set anywhere between 69 to 411 seconds with a frequency of between 0.0145 Hz to 0.000243 Hz. Next, we have three figures in this slide. So figure 2.4 is the MAX 30102 sensor. So this is the sensor that I'm going to use in my project. Figure 2.5 shows the pin configuration of the sensor. So it has 14 pin configuration. So in this project, I'm going to use the SCL pin that acts as the I2C clock input, the SDA pin that acts as a I2C data, and the ground, which will be connected to the ground, and the VDD that acts as the input. Okay, so this figure shows the principle of blood oxygen saturation and pulse measurement. So the sensor works on a concept of absorption of red light and infrared light, and the photodiode here, it converts the light into current. So this would be the previous researches that had been done, which is related to my project. So the first research is the clinical cause of COVID-19 patients needing supplemental oxygen outside the intensive care unit. And in this study, they have focused on patients admitted to a typical ward with hypoxemic respiratory failure. So the second research would be the design of smart pulse oximeter using ATmega 328 microcontroller. And in this research, oximeter sensor and LM35 sensor has been used. So the pulse oximeter sensor and the LCD would be activated by the configured microcontroller, and the result would then be displayed on the LCD and then transmitted to the Terra term through Bluetooth. So the third research is the design of COVID-19 stage alert system to ensure healthcare capacity with minimal closure. This study has been used stochastic SEIR model, and the use of stochastic optimization is to identify the policy triggers dictating stages of community mitigation. The fourth research would be the pulse oximeter usage in patient COVID-19 treatment. So here, the methodology is a finger is placed in a pulse oximeter to measure the oxygen saturation. The red light and the infrared light emitted from the oximeter are then reflected onto the blood to measure the SpO2 level. And the last research is the bradycardia in patient with COVID-19. And here they have used the EPIC electronic health record system. And the methodology for this research is the 4 patients that have been tested for COVID-19 pneumonia are required incubation and mechanical ventilation due to severe acute hypoxemic respiratory failure. Now I will explain on the PSM1 workflow. So this figure shows the flowchart of the PSM1 workflow. So first I have identified the project's aim, objective and the scope of study, and I have done with the literature review and the methodology. So the methodology consists of 3 parts, which is the software development, the hardware development and the performance evaluation. So the software development includes the circuit designing and programming. So once the circuit has been designed and the programming is done, I will be testing for the function and the errors. If let's say the error occurs, I have to troubleshoot it again, and then I have to test for the error again. So same goes to the hardware. So for the hardware development, I have developed the prototype and I have to perform the testing. So if let's say the device doesn't function, I have to troubleshoot it. If the device functions, it will undergo the performance evaluation, and I have to obtain a precise result, an accurate result for this project. If let's say I didn't manage to obtain an accurate result, I have to troubleshoot again in order to get the best result for this project. Next would be the block diagram for this project. So the block diagram consists of the MAX30102 sensor, the Node MCU ESP8266, the OLED display, the buzzer and the ThinkSpeak as the output. So based on the block diagram above, the Arduino Integrated Development Environment IDE will be used in this project. So the MAX30102 sensor is then connected to the Node MCU, and then the OLED display, the buzzer and the ThinkSpeak will also be connected to the system as the output. So the heart rate and the oxygen saturation reading will be displayed on the OLED display, and the data will be analyzed through ThinkSpeak, and then it will be displayed on the laptop or the PC. So if the reading of the oxygen saturation is more than 92% and the BPM is less than 60 or more than 100, the buzzer beeps and the users will receive notification as an alert sign. Next would be the software development. So this figure shows the flowchart of the proposed system. So first we have to place the finger on the MAX30102 sensor, and then the connection between the Node MCU and the MAX30102 will be initiated. If let's say the connection is successful, it will proceed to display the heart rate reading in BPM and the oxygen saturation level in SpO2 at the OLED display. So in this project, I have implemented 3 conditions, which is if the SpO2 is less than 92% or the BPM is less than 60 or more than 100, the buzzer beeps, and then the database will be analyzed from multiple inputs using the ThinkSpeak, and then the alert notification will be sent to the users. So next is the connection between the Node MCU, the MAX30102 and the OLED display. So this is the flowchart of the interface between the 3 components. So first I have to connect the component and initiate the Node MCU ESP8266 by installing the CH304G driver. Then I install the MAX3010X library and Adafruit SSD1306 library in Arduino. Later on I selected the driver port on Node MCU board, and then I created the coding. Once I compile the coding, if the error occurs, I have to troubleshoot the errors, and if the coding is fine, then I will upload the coding and into the circuit and carry out the function testing of the components. Then the MAX30102 sensor turns on, and the reading of the SpO2 and BPM is displayed on the OLED display. Next slide would be about the connection between the Node MCU ESP8266 and the ThinkSpeak. So first I have to initiate the Node MCU ESP8266 by installing the CH304G driver, and then I have to add the ThinkSpeak's library in the Arduino and create the coding. Later on I have to insert my network SSID and my password. Once done with that, I have to insert my channel's number and my channel's API key. Before that, I will be creating my channel on ThinkSpeak, and then I will compile the coding, and if the error occur, I have to troubleshoot them. If the coding runs fine, so I have to upload the coding to the circuit and then carry out the function testing on the ThinkSpeak, and the data will be displayed on and analyzed on the ThinkSpeak channel. So this shows the example of the interface of the proposed system on the ThinkSpeak. So I have created my channel in which I have two field chart. One is for the heart's BPM reading, another one is for the SpO2 percentage. So next would be the prototype design that I have designed by using the Tinkercad software. So this is my prototype design. This would be the OLED display, which acts as the display screen, and this is the body of my device. So inside here, I would include the Node MCU and the sensor. So this is the place where users are supposed to place their finger. So the dimension of this prototype would be 4 cm by 8 cm and 5 cm. Next would be the performance evaluation method. So the validation method is to compare the result of the developed oximeter to the pulse oximeter in the market. So the definition used to determine the SpO2 accuracy of the pulse oximeter is the root mean square, ARMS, difference between the measured value SpO2 and the reference value SRI. So the accuracy of the SpO2 is given by the pulse oximeter equipment should be ideally less than 4%. So if the reading differs by more than 8% or to 10%, it means that the test is considered inconclusive. So this is the formula that will be used to calculate the root mean square. Okay, next to the preliminary result. So this is the single sensor connection and testing. This is the circuit design that I have made, and this is the circuit connection that I have made by using the components, which is a Node MCU, the MAX sensor, OLED display, a buzzer, and the connecting wires on the breadboard. This will be my function testing of the components. So this figure 4.2 shows that the function testing of MAX 30102 sensor. So as we can see that the sensor functions well. And then this figure 4.3 shows the functions of OLED display that showed the oxygen saturation and heart rate value, but the values are kind of inaccurate because I need to do some changes in the coding. But as usual, the MAX sensor and the OLED display functions well. And this is the interface of Node MCU with ThinkSpeak for the SpO2 reading. So this is roughly the reading that I have obtained, but it is also inaccurate as there are changes needed to be done in the coding wise. So next to the future work. So the future work that is required in this project is to develop the alert system for multiple sensors that can be utilized in the COVID-19 ward. So the circuit would be rebuilt and tested with the coding to ensure that the system functions perfectly, and the ThinkSpeak will again be designed well so that it is enabled to receive the data of oxygen saturation and heart rate from multiple patients by using multiple sensors, and to analyze the database and send out an alert notification at the same time. Thank you.